So, bonjour and welcome to section 6. In this section, we will address some of the major scientific and technological challenges for research in AI for humanities. In the previous section, we discussed about important issues, bias, equality, inequalities, and transparency, future work, and all these kind of things. And this section is important because we believe that we have to address research for AI for humanities. Research for AI for humanity should be different from general research in AI. So just a few words how we organize this session. Junichi will give a brief introduction to this important topic of research for humanities. Then we have 5 speakers, 5 talks, each talk 13 minutes sharp, and questions, discussion will be at the end after the 5 talks. So welcome and enjoy the session. Junichi, please.
Okay, so this session is about next big challenges in core AI technology. It's a quite broad topics. When I took up the session chairs of this session with Fei-Fei, Stanford. We decided not to focus on very specific one topic, but we invite distinguished speakers and ask what they think the next big challenges in AI. So we decided to invite these 5 speakers in this session. And obviously, AI technology has made big progresses in these, let's say, 10 years. But that is mainly because of the progress of machine learning and deep learning in particular. Based on big data and also based on big computing firepower. But obviously, that technology have, I don't say defect, but lots of things which we have to solve in order for that technology to be widely adopted in the society. So in this session is focusing on not deep learning or machine learning per se, but what's the next step to move forward to address some of the problems of the current technology has. And in my field, for example, natural language processing and so on and so forth, when I started, there are several major problems. And some of the problems have been solved, or not solved completely, but made a big progress by using deep learning type of techniques. But obviously, many problems which we were interested in, let's say 20 years ago, are still not be solved. So this session would be how we can reconnect those topics with the current technologies like common sense reasoning, self-awareness, and transparent mechanism of intelligence, and how we can capture causality in the big data and so on and so forth. So we start this session by Andreas Dengel from DFKI. So you have 13 minutes. It's very short, but...
Do my best. Yeah, good morning, everyone. I'm excited to be here. And if you talk about the next big steps in AI, it's a broad field, and there are many things to talk about, but I have only 13 minutes. So therefore, today I'm concentrating on some aspects which are on a big demand these days, namely on deep learning. I'm directing DFKI now for more than 25 years, and at the beginning we were hunters for data. Nowadays we are overwhelmed with real problems from industry, which come up with big data from life science, from production and medicine, many areas. And so many industry partners also ask us how to proceed. And of course, they want to know a bit more about how their systems behave at the end, how the solutions would work. And as you know, we have many AI technologies which have, on one hand side, a kind of qualitative dimension. On the other side, they have ways of explain. And there is this big trade-off between these various methods. And since deep learning methods nowadays are outperforming many other methods, these are the ones which are mostly demand and also from the practical issue very easily to apply. So I'm going to concentrate really on explainability of deep neural networks. And if you look around what's possible, we have this black box problem. By the way, we had some problems in transforming the format, and therefore it's the old format of my own slides. We have these black box problems, and there is as you know, the demand for transparency and comprehension of what's going on. And of course, two fields, namely interpretability, to have a closer look into what might be observed with respect to cause and effect. And on the other hand, we have the field of explanation to give insights into the inner function of a system, which means at the end that we have to reveal some dimensions, like to get at least some visualization of which data is responsible for a forecast, for decision making, even more how this process is going through the network, somehow at the end to provide an explanation which could be monitored, traced, which is reliable and also somehow expressive enough. There are many questions in this context which we could ask. Yeah, so for example, which part of the input data causes decisions, how much diversity is present in the network itself, etc., etc. So many more like the ones I mentioned, but I'm going to answer some of those today. And please pardon me, in order to answer, I'm also a bit more technical for those who are interested. I think first of all, since this entire portfolio of deep learning has grown a lot, we need some orientation, some landscape where we have these multidimensional aspects of deep learning present somehow. And in this respect, you have input signals on one hand side ranging from text, pictures, videos, satellite, whatever. You have different network types. You have tasks to be solved, classification, translation, etc. You have the architectures, you have the components, and easy to be used, you have the tools. But it's like a jungle for many people who are not the experts like maybe you and me, but they want to know what's going on. And one aspect is also, this is just an example, that you could provide a faceted way to enter into such a domain, to have clicks, to get an orientation about best practices, what tools are supporting which architecture to solve which tasks, etc. And I think as this field is growing for more and more domains, we need such a landscape, an orientation to not invent things from you, to give students an orientation, especially all these companies we discussed last night about it, who are distant to AI, to get some kind of hint and some way to do it. Moreover, I'm also convinced that we need to understand how deep neural networks employ information. We talked about bias, and as you know, there are many different architectures, and they behave in some way different, and at least we have at the end hopefully some options to also debug and interpret and also reason about the results. As you know, basically deep neural networks are pattern recognizers, so they are trained to recognize those patterns which we want that they should recognize, but they don't have a holistic view, so it's easy to somehow manipulate them so that you enter some noise into that, some adversarial noise. and therefore get a different results. And this holds also for fields which are classical, for example, traffic sign recognition, which is not a new field, but more and more deep learning is applied to that, which usually should classify a traffic sign on demand of an autonomous car. But if you think about training different signs, like the priority sign in this case, shape it to the stop sign and maybe put it on slide, and then just enter the slide on top of the traffic sign, yeah, you might at the end come out with a different result, which is a problem. Yeah. Therefore, we should also ask how we could avoid such a situation. One option is to build or to use networks to explain networks in a better way. Some option, just to show you, is to use autoencoders, which are trained on big data sets. I don't go into the details. And you can use these autoencoders as a front end to classifiers, different classifiers, which behave different in a certain way, which you can use to feed the reconstruction images to the autoencoders to measure the prediction loss, and then somehow do backpropagation to see what happens. So, and as a first result, which is important, as I told you, I don't go into detail, we can also see the effects happening on the images and compare the classifier itself with the result with the reconstructed one and the effect of this training. So if you look at the lab model, which is based on luminescence and also the color change between green and magenta and between blue and yellow, you can see there's a certain histogram for all these dimensions. And if you look at the effects which happened, then you can see, based on this kind of using the autoencoder and the reconstructions, you can see that there is a certain way these networks behave. Most important, beside the histograms, is that you can also see that there are some checkerboard patterns inside these networks, which means at the end that they behave in a certain way, systematic. So, and also this reconstruction at the end has less information and which are transformed to the classifier, the classification results are about the same. Yeah. Which means that we can understand what information is used from the input signal by the classifier, which one is important. And therefore we find out that in some aspects only 50% of the information is used. Most important, we also know which one. And therefore, we can avoid situations like at the beginning with this adversarial noise, and instead of that, we can also build some filters as electronic shields, which are trying to avoid this manipulation themselves. Furthermore, I'm also convinced that there is a requirement to find ways to engineer deep neural networks. As I told you, these days, it's easy to use a standard tool with a standard architecture, apply, and you have reasonable, even very good results at the end. But we don't understand the internal structure good enough to do so. And therefore, if we understand it in a better way, we can also engineer these networks. If you look, for example, as in one of the fields which is of emerging interest for industry, we have right now about situations or use cases where we have 6,000 hour tests of engines with about 200 parallel data streams. And there are effects, correlations between these data streams that have to be measured. Yeah, if something happens like an anomaly, like in this case, an emergency case, we like to understand why this happens. And as you know, we have this end-to-end learning where it's hard to get the insight in the features per se, and even more also to know about even the features are extracted, how to understand and interpret them. So in such a way, we are trying to measure the influence of individual input on the inner structure of the network, but also on the output. And we can do this by just using the various input streams and consider their influence and the mix of the input streams as an influence to the anomaly sequence. And then we can visualize this influence in the input data on the various aspects and also see the correlations. More important is also that we can see the various filters used in the network themselves. There are hundreds, even thousands on a layer. And we can try to also learn through backpropagation the importance of these filters with respect to results. Some of them are standard, but maybe they have no effect. So we're trying to measure these effects and even then try furthermore to cluster these filters based on their behavior in different groups. Yeah? And based on these clusters, we are able to select the most important filters out of them. Which brings us to the effect that we can tune the network somehow, just concentrating on the most important filters here, and therefore even receive better results at the end. So this means now we can measure the influence somehow from the data to the output and also internally. And this is also a way that we can maybe transform this understanding of a network into a narrative explanation, which might be of importance. And therefore, we combined, oops, sorry, there is some mistranslation. So we have the input signal, and we have this influence tracer in the middle, and we have here statistic extraction of the input signal, and here we have a special sanity check, which is verifying the validity of this decision of the influence. And furthermore, we are generating text through special rules and also text generation and transform the input into different levels of explanation, trying to give maybe an expert view, just to give a hint what happens. And furthermore, we can also deeply explain the different correlations, what might cause such an emergency case. And this also means at the end what we discussed yesterday, that in such a situation, the system could initiate maybe a reaction, but also could ask back, based on my explanation, what should I do? Yeah, and that's my input. Thank you very much.
Thank you. Thank you. Thank you, Andrea. Oren, it's your time.
Hi, I'm Oren Etzioni. I'm delighted to be here. Sorry to take my jacket off. It's hot. Maybe it's all the hot air of talking about AI. So what I wanted to talk to you very briefly and to leave time for discussion is this challenge of trustworthy AI. And I think what I will present actually is a slightly different point of view than some other folks who think about it in the field. First of all, let me go back to the question that was raised yesterday. Do we all agree about what AI is? And to make it concrete, I'm going to talk about AI as it's practiced today in virtually every paper that gets submitted to academic conferences and many of the AI systems. And this AI consists of 3 steps. These are really deep learning systems. The first step is you gather an enormous amount of training data, whether it's from Twitter, images like ImagineIt, European Parliament proceedings that are in multiple languages. This data is typically labeled, meaning that each data point is a vector in some form, and associated with that vector is a label of a category. This is a cat, this is a dog, this word is in English, this word is in French. You then apply deep learning, which is a set of techniques loosely inspired by the brain, which design networks where there are many simple nodes that are interconnected with edges that have weights on them. These computational mechanisms boil down actually to matrix multiplications, vector operations, 3-dimensional matrices called tensors in the machine. So if you look down below the metaphor of a neural network, we are really doing multiplications, additions, and weight updating. But what's exciting is that this approach has actually led to impressive gains on virtually every task that AI people have attempted, whether it's game playing, visual tasks. I remember just a few years ago, people were saying, well, natural language is different. Tasks that involve words and sentences, like understanding the meaning of the sentence or translating it or deciding whether this is a positive sentiment or negative sentiment, all those sorts of things, people are saying, well, that's quite different than images. This approach might not work. Well, I'm here to tell you, it works just as well, if not better. And we could get into a whole tutorial about why that is, but that's not the topic of my talk. So despite the fact that this quote-unquote works, it's actually not trustworthy in some very important ways. So if I can use this machinery, I'll illustrate this for you. So here is a picture. And if we look at a region in the picture, this may be hard to see, but we apply our visual recognizers, we can start to see, this is a visualization, that what does this sort of look like here? Anybody? A car, thank you. Right, so I'm not sure whether that's funny, but I appreciate it. So in fact, we've taken a signal, we've amplified it, we've made it sharper, and sure enough, this looks like a car. The problem is that that region was taken from right here in the bigger picture, right? So in context, we see that it just looked like a car locally, but it's probably not a car, both because of the size and the more general context. This is very typical behavior for deep learning. If we look closely and we look at the behavior of the network, we will draw one conclusion. If we zoom out, turns out that we are wrong. This is by no means only the case with vision. So here's an example, and this is from some demos that are on our website. Our website is alanai.org, and we have many demonstration systems, vision systems, natural language processing systems, and so on. And this is a famous task called reading comprehension. Those of you who may be familiar, it's from the Squad data set. And we gave it a paragraph about the movie The Matrix. And we ask it questions like, who stars in The Matrix, to answer based on the paragraph. It doesn't quite read, even though this is called reading comprehension, but what it does is it highlights, the way you might highlight with a marker, you highlight the span that corresponds to the answer. So if I ask it the question, wait, sorry, let me go back. If I'm able to. This one goes back. No, the red one goes back. Okay, so if I ask it who stars in The Matrix, it highlights the span of text. Hopefully you can see Keanu Reeves, Lawrence Fishburne, etc. This is really quite nice. It was trained, by the way, it hasn't seen this paragraph before. It was trained on other paragraphs, etc. I asked it, what is Neo's profession in the movie? And again, this is even more impressive because it doesn't explicitly say that Neo's profession doesn't use the word profession, but it comes back here and highlights computer programmer. It says computer programmer, Neo, et cetera, et cetera. So it realizes that computer programmer is a profession and it's attached to Neo. If I go a step further, and this is, I actually went through this myself, playing with this and tried to break it. And so I asked it, what's the machine's goal? Which is a pretty abstract question here. And oops, sorry, again, not used to this. And it says here, I don't know if you can read, it says to subdue the human population. And at this point, I was like, whoa, maybe we discovered artificial intelligence, you know. I was, this, of course, not programmed to the machine. I was really impressed with the answer. But I said, you know, let's kick the tires a little bit more. So I asked the question, who is Neo fighting? And the answer was computer programmer. So all of a sudden I've realized what I think most people have realized if they've spent some time with Alexa or with Siri and so on. These systems are very brittle. You can ask a question and get a wonderful, precise, on-target answer. And you can ask another question that seems very similar to us. Surely if it knows A, it can answer B. And you can get another answer that shows that the machine does not understand what's happening in the paragraph at all, right? Who is Neo fighting has nothing to do with the answer, computer programmer. I asked it how many actors star in The Matrix, and again, it realizes I'm looking for a number. It found the year that The Matrix was played at. So you have to be very careful with these AI systems. On the one hand, they're quite capable. On the other hand, they're very brittle, and as a result, they're not trustworthy, right? However powerful they may seem, I would very much hesitate, right? We have these new results in medical systems with, for example, diagnosis of images, superhuman performance. I would not want myself or my child diagnosed by a machine, not without some careful checks and balances. And of course, this has implications to autonomous weapons and other issues as well, right? They can be super targeted, but periodically they make a mistake and they blow up, I don't know, the 5th arrondissement. Depending on how you feel about the 5th, it's, anyway, not a good idea. So what is going to make AI more trustworthy in the future? One I've already mentioned, this notion of robustness. How do we make it more resilient to errors? A second one is improved explanation and transparency. And I should mention that in this case, I'm a little bit less sure than some of my colleagues that we know how to do that. It turns out that taking these very complex systems and building an explanation of them, of their behavior automatically, is extremely, extremely difficult. It may actually even be impossible. So I'll talk in a little bit about a different approach. How much time do I have? I think 3 minutes. Okay, and I will talk fast. And then the last thing is thinking way ahead about the issue of safety. People like Stuart Russell and Nick Bostrom and others have brought up, as these AI systems become more powerful, how can they be safe? And our fundamental contention is to do better at all these things, these systems need better background knowledge. What they really need is some notion of common sense knowledge, basic common facts, some notion of what's happening in the world, some notion of people's reactions. Because I'm essentially out of time, let me illustrate this with a simple example. In the late 80s and 90s, I worked on softbots. These were software robots, they were agents supposed to make it easier for you to use your laptop or your phone. And I would be able to say to my softbot, reduce my disk utilization by 20%. Seems like a nice thing instead of having to futz around with compression and moving files around. I'll just tell my softbot, my assistant, to do it. It'll come back 2 minutes later and says, Dr. Etzioni, I've reduced your disk utilization by 25%. I say, excellent, explain yourself. He says, well, I took your grant proposal and all these voluminous data sets that support it, I deleted those. I say, well, you saved the backups. No, I deleted the backups too. They took up a lot of space, but now your disk is in good shape. So now why would the softbot not do that and destroy 5 years of research, right? It has to have background knowledge about that I need that data for the grant, has to have common sense that I wouldn't want it to do that. But where would that come from? Current AI programs, even today, don't have that information. I was told not to stand there, so here I am. I apologize. So it's really essential for these programs to have common sense. I'll just give you one more example from the medical domain. Let's say a patient is being wheeled into surgery to compute the dosage of a very toxic drug. We're going to trust the infallible computer algorithm to compute exactly the right dosage. And they look at the data. It's a 5-year-old patient. She weighs 700 kilos, and we compute the exact right dosage of the drug. And we need a person in the loop to stop and say, wait a minute, does it make sense that a 5-year-old will weigh 700 kilos? Maybe there's some mistake in the data input. Stop before you kill the patient. So my point is that we cannot just rely on these black boxes. even on their potential explanations, we have to have a human in the loop in the right way, and we have to have them developing some common sense knowledge. This is a picture of my colleague Yejin Choi, who's working at the Mosaic project at the Allen Institute for AI. She shares her time between us and the University of Washington, and she's leading the charge on a new project to acquire common sense knowledge. My last slide, because I'm out of time, is what do we do in the meantime? Common sense knowledge is a very hard task, so we're still using AI programs. In the meantime, what I advocate is auditing AI programs. Imagine that any AI program, it's not that we require it to provide detailed explanations, we require it to be able to answer questions about specific cases. The best analogy I can give you is if I want to understand the emissions of a car, I don't ask for a full explanation of how the engine works and so on, but I do stop at a test station, and hopefully I'm not Volkswagen and I'm not cheating. And at the test station, I check what kind of carbon dioxide the system is emitting. So I can imagine the same sort of thing. I have a loan processing program, and I give it a case, and I check to see that the program is not racist. I can talk about this in more detail later. Thank you very much.
Thank you.
Thank you. I'm Marcel Hébert from Carnegie Mellon University. I'm going to talk to you today about some questions related to use of AI in robotics and autonomous systems. And I'm going to do so based on my experience as a professor in the Robotics Institute. But before I do this, let me put on my other hat, which is as Dean of the School of Computer Science, to relate to the previous panel and to say basically three things. First, to emphasize again the importance of diversity in tech education. Second, and I take no credit for this, this is bragging on behalf of the previous administration, to mention that fully 50% of our incoming undergraduate computer science student is female, and then to say that we're aiming to do so in the next few years for the graduate students as well. So moving on now to the topic of the day. I'm going to talk to you about AI for robotics and autonomous systems and looking at some of the key challenges that we are facing. So when we're talking about robotics and autonomous systems, we're talking about systems that have to be very safe. The word at the title at the top should say safe. It has been changed. This is an example here from an autonomous car from Argo AI. Operating in a real environment fully autonomously, it has to be, of course, extremely safe in the presence of pedestrians, other cars, etc. It has to be fast. Fast doesn't just mean being able to compute things fast. It means being able to compute things with a limited computing budget, limited power, limited communication. This is an example here from a drone flying at high speed in very cluttered environment, having to make decisions in real time with basically a decision loop of below a millisecond. It also has to be work in very complex configuration. We tend to think sometimes of robotics and autonomous systems as systems that we used to from an anthropomorphic standpoint. Cars, humanoid things, etc. It can take very, very different form that cannot use the intuition that we have as humans in designing those systems. So what all of those systems share in common is the need to learn models, visual models, decision models from data. And in particular, to do that mostly in a supervised manner, requiring enormous amount of data that is curated, that is prepared, that is humanly annotated. So one of the big challenges is how to learn models with minimal supervision. For example, instead of going directly from supervised data to model, to look at having learned many models offline, for many, many tasks, and be able to, instead of learning from data, learning from experience, so that we can now, at runtime, be able to adapt the model from very few examples. That is the area of meta-learning, learning to learn, and those kind of things. that is not very satisfying because we still need a lot of data. We still need a lot of supervision. A more appealing approach would be to do what this child is doing in this video, which is basically to learn by interacting with the world. The thing we have going for us in robotics is that we actively interact with the environment and we can learn from those interactions. Like a child here trying to manipulate objects for a long time until it works. This is an example here from Abhinav Gupta of a robot trying to grasp object. It will do this thousands and thousands of times over hundreds of hours. It's a very depressing sight, by the way, as you can imagine, to watch. Once it's done that enough, it can do this. So it's going to grasp objects. Those objects are not particularly exciting, okay? It's not a particularly exciting grasping operation until you realize that it has never seen those objects ever, and nobody has ever programmed this robot how to grasp objects. So this is what self-supervision is. So that's nice. We're making progress there in minimizing supervision, but this is still kind of manually programmed. Somebody has to tell the system, this is what I'm interested in. I'm interested in grasping. I'm interested in pushing or whatever. What the next step would be to have the system itself discover what are the interesting actions to do, the interesting things to learn. That's implementing basically this concept of curiosity and basically exploring the space of stuff to do. This is, for example, what this child is doing, not having a goal in mind necessarily, but just exploring its interaction. We start to explore that in robotics. This is what is called curiosity-based learning. This is an example here from Deepak Pathak, where the robot initially does some random things and then realizes what it should be looking for and eventually gets to the point where it by itself learns things like touching, like pushing, like grasping without anybody having ever programmed the robot to look for those things. Okay? It takes a very, very long time, by the way, in terms of trials and computation to get to that point. So don't misunderstand me, this is not yet practical. Okay? So I talked primarily about autonomy, about robots operating autonomously. Of course, in reality, robots have to operate with people. And this leads to the next big topic, which is human interaction. This is an example here. Now, this is a very misleading example in the following sense. It looks very simple. Right? It looks like a kind of a boring example, right? An industrial robot handling a couple of tools. This is actually very hard. It in fact encapsulates all of the problems in human interaction. The safety problem. This robot has to operate in extreme proximity to a person, and it has to do so still carrying its task, not just stopping. You know, the safest way of operating is to do nothing. Right? That's guaranteed to be safe. Okay? The difficult way of operating safely is to actually carry out the task while guaranteeing maintaining safety. The second thing that it illustrates is the need to understand the person's behavior and the person's intent. Even in this case, there is a very simple interaction, basically, of handling a couple of tools. So what do we need to look at here? Well, we need to do two things. We need to be able to model and represent behaviors and intent, not just what a person is doing now, but what the person is intending to do. Second, the ability to now share decisions or share autonomy between the person, the operator, the core robot, if you will, and the autonomous system and the AI system, which is an even harder problem. This is an example here in the context of pedestrians in a street. The little colored lines here indicate main modes of prediction for this person walking there. This is done entirely from videos. Now, again, this is one of those things that looks simple and looks kind of obvious. Well, obviously, that's where this person wants to walk. It becomes much harder if you realize that underneath that there is an entire probability distribution of where the person is likely to go in the future. And even more than that, if you want to use this for autonomous systems, you need to update this probability distribution at every decision time, perhaps every millisecond in the example I showed in a self-driving car, for example. The problem gets even harder when you consider that now this person is not working by himself in this scene. It's actually working in the middle of many other agents. And then you run into the problem, the basically game theoretic problem, that how this person works, the decision that he's making, depend on how the other agents are working, and vice versa. The way the other agents are working depends on how this person is working. So you can see how this problem basically blows up exponentially as we go closer and closer to the realistic type of situation that I showed in my opening video from Argo. The second thing we need to do is to interact with humans, and this is, again, a deceivingly simple example here. This is a human subject experiment from Professor Heni Admani at CMU. Here, the subject is asked to do what seems to be like a very simple task, which is to pick up this object in this ball by teleoperating the robot, joysticking basically the robot. Now, this looks simple, but it's not, because the robot does not respond exactly as it's controlled. There's delays in the system, et cetera, as usual in those kind of tasks. Now, it's going to take her a very long time to do this. It's going to take her almost a minute, so I'm not going to let it go until the end, because I'm going to be yelled at in terms of time. So it takes about a minute for her to complete this seemingly simple task. Now, instead of that, what we can do, oops, that was bad move right there. Yeah. Instead of that, what we can do, maybe. Okay. Instead of that, what we can do is to share autonomy with the person. In this case now, there is an AI system behind assisting the person that's looking at her gaze, looking at her motion, looking at her head posture, and so forth, to guess her intent, what task she's trying to do. And now she can complete it in 13 seconds, about 5 times faster, by having the AI system sharing autonomy with the person by guessing her intent and trying to help her. Now, this is a very simple example because it's a human subject study. You can extrapolate now how this can be used to assist drivers, how this can be used to assist other types of control. All right, so learning from limited data, human interaction, making decisions and so forth, those are some big problems. The last one is basically, well, how to make all those systems reliable, trustable. There was already a lot of discussion of that in Oren's talk in particular, so I'm not going to revisit things like explainability, common sense, and all those things that apply here too. But the basic problem when you're talking about autonomous systems now, where you have to go into a 2-ton object and basically trust that it's not going to kill you, we have bigger issues to deal with. And I would mention 2 things very quickly. One is this issue of self-awareness or competency awareness, which actually is covered by major national research programs now. And basically what that means is the ability for the system to assess its own performance. So to take a very stupid example, if you're driving and suddenly you are surrounded by fog, you instantly know that your visual system is impaired, and you instantly drop into a different behavior, meaning you slow down. There is no understanding or explanation as to why this happened, as to exactly how it affects your visual system. You just have immediate awareness that your performance are degraded. We don't know how to do this, even in the simplest form for autonomous system. That is a major issue. And the last thing I will mention about this, we talked a lot about explainability. For autonomous system, and this is maybe a debate we can have offline, for autonomous system, I don't think explainability is the main issue. If I walk down the stage here, since I'm sober today, I'm not going to fall on those stairs. I'm just going to walk down the steps. I'm going to be able to negotiate those steps. I cannot explain how I do that. I cannot explain the steps, the cognitive steps that are followed for me to go down those steps. But you can predict that I'm going to do this correctly because I'm a human being and I'm apparently in reasonable health, and you know roughly what I'm going to do. That's what we need to achieve for autonomous system. In other words, predictability, or at least predictable measurable performance rather than explainability. And I am exactly at time, so I will leave it at this. Thank you.
Thank you. Thank you. Thank you. Thank you, Michael. Again, please.
Bonjour, everyone. It's a great pleasure to be here and to have the opportunity to share my thoughts on a problem and a possible solution to that problem, which I think nicely relates to some of the issues pointed out to the previous speakers here. So the problem that I want to talk about is what I call the talent bottleneck. And to basically make you understand what this is about, let me first of all say it has been stated before that success in creating AI might be a scary thing indeed. Not just a big thing, the biggest event perhaps in human history, might also be a really problematic thing. The late Stephen Hawking put it into these words. I'm sure you've seen that. I'm sure many of you think that's a little alarmist. But you know, he was a clever man. I think he demonstrated in many ways that he could look far ahead. And so, as a result of that, of course, we've been thinking about, you know, what are really the big risks of AI, and what we've been very much focusing on, pushed by people like Stephen Hawking. I think, you know, even people with a little bit more insight into the subject matter, like Bill Gates, for example, has joined that bandwagon. Fueled by Hollywood, we think that strong AI going bad is the thing to be afraid of. Well, actually, no. That might be the thing you want to be afraid of 50, 100 years out, and I am firmly with those who say, when is the right time to worry about, you know, some big asteroid hitting Earth? Is it now? Is it 50 years from now? Is it 100 years from now? It's probably now still, right? But the much more pressing problem is this: incompetent use of weak AI, right? That is the problem that we're going to see cause a lot of issues within the next year, the next 5 years, the next 10 years, and I would hazard a guess even within the next 20 and 30 years. So let's take a step back about 150 years to the dawn of what we would call the age of machines. So here, of course, we see Charles Babbage, the father of computing, the guy who first realized that universal computation, computers that in principle could do anything, would be not just an exciting thing to have, but also, you know, extremely doable. And as you might have heard, the main reason why he didn't succeed was not because technology 150 years ago wasn't up to the task, but it was more or less because he didn't get the funding to pursue his vision. However, he had a strong vision. He knew that as soon as something like a universal computer, he called it an analytical engine, would exist, it would necessarily change the nature of science. And his contemporary Ada Lovelace went a step further to realize that it would actually change everything. This was based on a very interesting view of what computation, the very thing underlying AI and all of information technology, what that actually is about. And what it's about, in a nutshell, is clear and precise instructions that are flawlessly executed, right? When we build computers, the goal is to have them operate absolutely flawlessly in predictable manners. And that's why they've been so amazingly effective, not just because they automate things, but because they can do something that humans have immense difficulties with, right? Humans individually and in groups are not good at following flawlessly clear and precise instructions. They're not even very good at giving these instructions, which is what makes programming hard. So this is the very notion of an algorithm. And when we talk about AI, this is actually what everything ultimately is built upon. Now, of course, we live in a world where algorithms control almost everything, right? However, something else has happened that changes the game, and it's been mentioned by others before. Something that I think we're justified to call a revolution, the machine learning revolution. And what is that? Well, what that really is, in my mind, is the automatic construction of algorithms that work well in given situations and given data, right? Machine learning is not so much about classification, about prediction. It is about the automation of programming, about taking that task of coming up with clear and precise instructions that are then flawlessly executed, taking this task from humans who are not very good at it, and having machines do that as well. The basis for that, as we know, for being able to do that, lie in statistics and mathematical optimization with very deep roots in both of these fields. And also that relies to a surprising amount on principled experimentation. The shift to machine learning makes computer science much more resemble biology, chemistry, other sciences, psychology, right, that have had that notion of principled experimentation far longer than computer science has had it. And of course, machine learning has been thought of from the very beginning. Alan Turing wrote this beautiful in 1950 as the key ingredient in artificial intelligence. However, machine learning is not all that's needed for intelligent behavior. And the easiest way to see this is that if you think about what we mean by intelligent behavior, It's, of course, human intelligence. It's the only notion that we meaningfully can have. And human intelligence is not just learned, right? It's much more than learning. It also critically involves reasoning. And that's actually what distinguishes us from a lot of other organisms that learn just fine, in some cases even better than we do in certain tasks. So now, of course, we have an age of AI, right? We have opportunities that come with that and challenges. Of course, the opportunities are manifold. They're of economic nature, but they are also of the nature that actually AI can help us not only do things better and more competitively, but also AI is, in my opinion, clearly the key to addressing some of the grand problems of our time. For example, climate change. For example, inequity. The problem is that this comes with risks that have been well articulated in other sessions. Job loss is one of them. Manipulation of individual and collective behavior is another one that we should be very concerned about. And of course, increased inequity due to a barrier of entry, right? And then there is the talent bottleneck, right? And the talent bottleneck basically means not enough people who are deeply enough qualified to do AI well. And if you combine this with the human tendency to overestimate anything that shows even a little bit of intelligence, you get a pretty toxic brew, okay? So AI systems are useful and lucrative, but they're also very challenging to build and to deploy and to maintain and to monitor once you have done that, once you have deployed them. AI expertise, there is great demand and relatively little supply. Of course, one way of addressing this issue is to make sure that we create more AI talent, more AI experts. My firm prediction is that this cannot be fast enough, at least not for the next 5 to 10 years, even if we go all out on it, which we should, because humans will still want to do more with that, and there will be this tendency to overestimate what can be done, and as a result of that, then you have a failure of these systems, you have limitations of these systems that go unnoticed until you see consequences that you really don't like, okay? So what you have as a result of this talent bottleneck is that you basically have underqualified people, experts that are not really experts, building, maintaining, monitoring, and maintaining systems that they don't really understand very well, and that results in low-quality AI systems with unknown limitations, and that causes all sorts of problems, which can be quite subtle and can be quite difficult to repair once they've occurred. So here's a nice article from earlier this year from somebody with a great background in software engineering, Patricia Herman, and she says, as a software tester, I question the safety of self-driving cars, and gives all sorts of examples where much simpler systems, for example, the MCAS system that we now know is responsible for the loss of 2 Boeing aircraft, highly sophisticated aircraft, how we are not even able to correctly foresee how these kind of things will work for all sorts of reasons, regulatory reasons, as much as technical reasons. So what can we do about this? There is a notion that has popped up recently that's very popular in machine learning. It's called automated machine learning. That's based on this idea that although machine learning is very powerful, actually doing useful things with it is highly non-trivial. And this causes a fundamental problem. You know, you have many available algorithms. You can set up these algorithms in different ways. How do you actually do this? And this is what machine learning experts know how to do, at least to some extent, and that's why they're very heavily sought after. An example for that doesn't even have to go into deep learning and the latest technology, but that applies to much simpler machine learning algorithms, is this Weka environment that some of you might have heard about, very prominent machine learning library still. Contains 39 classification algorithms alone, together with a lot of feature selection methods, and all these can be relatively freely combined. How do you choose which one to apply? And the solution that AutoML gives to that is to basically have an algorithm to do that. Have an algorithm find the right algorithm to use and its right configuration. And this is the notion of automated machine learning, or AutoML. So This achieves substantial performance improvements over solutions that are even handcrafted by human experts. This has been amply demonstrated over the last 10 years, and especially over the last 3 to 5 years. It helps non-experts also to effectively solve machine learning problems that otherwise they couldn't solve very well at all. And it's become an intense international research focus in academia and industry. So there is 2 lines of work that I was myself involved in, the AutoWecker and the AutoSKLearn project that's based out of Freiburg. But also giants like Google are now putting a lot of effort into this sort of auto-ML idea. And as I said, this has been demonstrated in various settings to outperform human experts, in many cases very substantially. Okay? And it's widely perceived to be at least one of the next big things in AI. So now there is an interesting idea that I want to share with you before I conclude. And this is to use AI to help to construct not just better machine learning algorithms, but better AI systems, which need many more capabilities than just machine learning, right? And that is what we call auto AI, the automated version of artificial intelligence. And it's really, the step is very similar to go from ML to auto ML that we will take to go from AI to auto AI. It's leveraging learning optimization and advanced statistics in order to do things that normally would take human experts. That will reduce the barrier to entry for humans in terms of building, maintaining, and deploying high-quality AI systems that are predictable, robust, and performance. And that will alleviate the AI bottleneck, but also help experts to do a better job and give broader access to AI, democratize the use of AI, and finally give it increased benefits at reduced risks. So my take-home message is very simple. AI is a revolution that has taken explicit programming, which is a job that people are actually not very good at, that takes a lot of discipline and training, to automatic programming. That is the revolution that's really happening in AI. The risk that we should be concerned about most is the incompetent use of weak AI. The lack of experience or expertise that will then lead to low-quality AI systems. And the solution to that, at least in part, is to use AI cleverly to customize the construction, deployment, maintenance of AI systems to basically amplify the expertise, the limited expertise that we have for the benefit of all, and that's auto AI. And that, I think, is a very realistic goal. You might think it's a pie in the sky, but in fact, the foundation for doing this work has been laid in the area of automatic configuration and auto ML, which already has shown a lot of traction. Thank you very much.
Thank you.
My name is Bernhard Schölkopf. I'm from the Max Planck Institute for Intelligent Systems. And our institute is devoted to the study of intelligence broadly. So I think I have a slightly different view. I don't see intelligence as limited to humans, as Holger, but I think we see it everywhere in the animal kingdom. And I have some examples here, ranging from a blood cell in pursuit of bacteria in the bloodstream, a frog trying to catch an insect, and then some humans, one of them doing parkour, very sophisticated visual motor behavior, and then finally some humans engaging in some complex collective intelligent behavior, in this case performing a double chorus Bach cantata that sadly you can't hear right now. Now, we are interested in what are the organizing principles of this kind of behavior. And of course, I think we all agree that probably learning plays some role in this question. So that's a strong contender for organizing principles. And I'll show you a page from the New York Times from 1958. So this was there was a report somewhere in the back on a new machine called the perceptron. And Frank Rosenblatt demonstrated that this perceptron was able to learn from experience, and he also predicted that later perceptrons will be able to recognize people, call out their names, translate speech into other languages. So this was probably quite spectacular, quite fantastic, these predictions. But if we now look back a bit more than 50 years, it's remarkable how much of it actually has come close to true, at least. So this, at the time, was the birth of connectionism, so the attempt to build synthetic brains. Now, we know that around the same time, another field was started, and we know the story didn't end well for Rosenblatt. On several levels of Rosenblatt tragically died in a boating accident. I think he was quite a kind of a flamboyant personality, doing all sorts of things. His field also died relatively young, and at the time, the field of what we now would call classical AI won against connectionism. Probably for good reasons. Classical AI really was the birth of computer science. There was this crucial insight that computers can do more than just compute with numbers. Computers can manipulate symbols more generally. People came up with the first high-level programming languages, etc. So this field of symbolic AI was very successful, and one of the heroes of that field, of course, was Herb Simon. Early on, the optimism was so large after the first successes that he predicted that machines will be capable within 20 years of doing any work a man can do. Now, we know that, of course, this prediction was remarkably non-true, and at some point, people got a bit frustrated with it. Hans Moravec found a nice way of putting things by saying that it turned out that the hard problems, such as chess or automatic theorem proving, were remarkably easy, but the easy problems, such as including everything animals can do, turned out hard for AI. Now, things have changed since then. Holger has already talked about that. We've seen a lot of machine learning entering the stage again, and it turns out that using machine learning, we can now finally tackle the easy problems, the problem that looked easy. And this is an example from my own lab, very recent, where we train a robot, a very hard-to-control robot with essentially synthetic muscles to play table tennis. And I think it is quite impressive, and it's a very, very difficult to control system that just with hard-coded algorithms we wouldn't be able to control. Now, machine learning turned out to be particularly strong whenever we have huge data sets. And without going into detail, I'm showing you one such example. This is an example from bioinformatics, where we're looking for a relatively complex high-dimensional signal. You see a learning curve here. And on the right-hand side, you see that for 10 million training examples, the performance is actually rather impressive. At the time, this was state-of-the-art, or better than state-of-the-art. So it's a regularity where you look at DNA sequences. It's something that a human couldn't see, that there's structure. For us, it would look random. But if we have enough data, it's totally non-random. So it's a kind of structure that a human cannot see, but a machine can find. And these kind of non-trivial inference problems we see popping up all over the place now. And they share some characteristics, so that they tend to be high-dimensional and complex. They concern applications or cases where we have little mechanistic understanding of problems. This is often the case in medicine, for instance. As a consequence, we need large training sets in all these cases. And there are theoretical results in statistical learning theory that tell us that we have algorithms that are optimal in the limit, that do the best any system could do, including a human, subject to assumptions. And one of the assumptions that's in the small print of these results is that we're working with IID data, so independent, identically distributed data. That means the regularity from which we draw data doesn't change. In particular, it doesn't change between training and testing. Now, this turns out to be a very non-innocuous assumption, and many of the problems that we nowadays see with machine learning are connected to this assumption, and I'll try to explain this problem a little bit and explain how it's related to causality. And I want to do this with this example here from, it's a slide I have from Pietro Perona, from object recognition. So we all know with deep learning we can get great performance in object recognition. We can recognize lots of different objects. We can recognize cows. In this case, very reliably so. But it turns out if we look at some cows that are no longer standing on a green meadow, so if there are things in the test image, in this case the beach or the sea, that are negatively correlated with the presence of the cow in the training set, then the systems don't recognize even a simple cow anymore. And the reason, of course, I already put it this way, the reason is that machine learning looks for correlations. It doesn't care about causality. And as long as you're guaranteed that the future looks the same as the past, so if this IID assumption holds true, independent, identically distributed, then it's perfectly reasonable to rely on correlations. If nothing changes, the same correlations will be there in the test data. Since these systems are so highly optimized to a given distribution, to a given data set, they are not robust with respect to violations, even in this case, very small violations that are not perceptible, violations of the IID assumption, not perceptible to humans at all. So this is the phenomenon of adversarial vulnerability, where we add a little bit of noise to an image. The image still looks the same afterwards, but then suddenly the system classifies this little pig as an airliner. I think to get more robust, machine learning should move beyond statistics and incorporate causal knowledge. And the first person to understand this was Hans Reichenbach. Here I'll show you this example. Reichenbach was postulating that if there's two variables that you find to be correlated, then there must be a third one that explains this correlation. This third one could coincide with the first two, with one of the first two. So if you find that storks and frequency of storks and the human birth rate are correlated, which is the case in Europe, then it could be that the storks bring the babies, could be that the babies attract the storks, or that there's something else that causes both of them, such as economic development. And the difficult thing now is that from data alone, we cannot distinguish between these three cases. And I want to show you, so we've studied this problem for 10 years now. And if we want to do causal inference, if we want to tell what is cause and what is effect from two-dimensional data, from just two variables, then we need additional assumptions. And one of these assumptions I can explain visually with this thing here, which is called a Bechet chair. So when we see this chair, our brain makes the assumption that the object and the mechanism by which the light from the object reaches our brains is independent. Now we can formulate this assumption like this. We can violate this assumption if we look through this very specific hole marked by the arrow here, in which case we see this object, which means we see an object which isn't there. So that means perception fails. So that means in the generic case, it's our visual system is justified to use this assumption that there is this independence, and this is used in various ways and discussed in various ways. It's called the generic viewpoint assumption. It's also related to something called structure of motion. So when we look at an object and move our head around it, even if we close one eye, we get an idea of the 3D structure of the object. And the reason is that we can safely assume that our perceptual process, in particular the direction of the viewpoint, doesn't change the object itself. So the object itself is independent from that. It doesn't change. It remains invariant as we move our head around it. So this kind of principle it's a principle about the causal generative structure of the world and of things that we see in the world. And it turns out we can formulate this mathematically and exploit it for inference, but that's beyond the scope of the current talk. So just very briefly, one application that we've worked on is in exoplanet search. It's a topic that I find particularly interesting. Exoplanet search, so there's this Kepler satellite that has been looking at 150, I think several 100,000 stars in the Milky Way, looking for exoplanet transits, looking for little dips in the light curve. Which then allows us to infer that there's a planet that has passed through the disk of a star. And we've built a causal model for this problem. It's causal in the sense that it's trying to reconstruct this confounder, the instrument. The instrument affects what we see, but we really were interested in the astrophysical signal. It's trying to reconstruct this confounder by looking at lots of other stars and setting up a causal model. We've done this, and with it, we discovered, this was a few years ago, 17 new exoplanets at the time. So I thought that was a nice application. And it turns out recently this application has become more relevant just by a strike of luck, since you may have read in the news or heard in the news, there was this, about a month ago, people found traces of water in a planet which is in the habitable zone around a star a bit more than 100 light years away. And it turns out that this was actually one of the exoplanets that was found in our study originally using machine learning and causal reasoning. So coming towards the end, I think we are in well, let me skip these 2 slides and rather tell you about this. So since we're in a session that should talk about where are things heading. So this question was asked in this recent study, Technology Review. You can see that certain topics are getting bigger, certain other topics are getting smaller. I think this is a fact. I'm not saying that I'm endorsing all these changes. I'm, for instance, quite close to theory, and I see that the term theory is going down, the term performance is going up. Maybe that's a good thing. Now, from my own, this is the last slide, from my own personal view, one thing that came out in the study is reinforcement learning is increasing. I think that's Martial also mentioned that. I think this is going to continue. Speaking in France, I probably should also make this point that Yann LeCun makes everywhere he speaks about the field, that unsupervised learning will increase in importance. And finally, adding my own perspective, I think we will see a merger of the fields of representation learning and causality. Because representation learning doesn't care about the structure. It doesn't care about interventional structure. It just models statistical structure in the data, whereas causality usually doesn't care about where the variables come from in the first place. So we have to learn what are the variables that are connected by causal structures. And we have to do this from raw data unless we are willing to program it in, and I think that's not going to work. So thank you very much for your attention.
Thank you very much. Okay, so we have time now for questions. Yes, please. You have the microphone.
Thank you very much for your presentations. It was a great overview of challenges at the technical level. The name of this panel is Next Big Challenges in Core AI Technology, and one of the speakers underlined the question of talent bottlenecks, and the key to addressing big challenges of our time, including inequity, is AI. You also underlined the need to create more AI talent and AI experts for better AI systems. I'm going to throw maybe a curveball question, because I note here that on the panel there are 7 men from the global north, and one big challenge in developing the future of AI technology is also changing the narrative about AI, but also particularly changing how we think about AI development, innovation, and deployment. So my questions directly to the panel is, as specialists and clearly technical engineers, what in your opinion needs to be done to address existing gender bias embedded in AI technology, but also gender imbalance in the AI field?
We have indeed, thank you for we have indeed a gender balance problem here, but there was a Fei-Fei lead that couldn't come, so the problem would be less important. Maybe Holger, you?
Yeah, so maybe I'll respond a little bit to that. You know, I fully agree that this is a big problem, and particularly gender imbalance in core AI worries me a lot. It worries me because it makes for work environments that, in my personal observation, and I've been heading groups that were 80% female all the way to 80% male over the last 20 years. I think it makes for poor work environment, these big imbalances. I also believe that we're missing out on a lot of talent. Another area where we're missing out on a lot of talent is within Europe, with this focus on you know the countries that are already strong in AI, right? I think actually one of the biggest exciting advantages that we have in Europe, and you can easily extrapolate this to other parts of the world, is that we have an enormous and very weakly tapped talent pool in Central, Eastern, and Southern Europe. So I see this not only as a problem, but also as a challenge and an immense opportunity. So in part of my non-technical work, as some of you might know, I'm very much promoting and running an organization called CLARE that is firmly committed to restoring a little bit more balance there. And the way I do that is by connecting the talent bottleneck as a key problem to the existence of these resources that we can bring and need to bring to the table. Now, there are many mechanisms that we can think of. One that I think is a little problematic is that what my colleagues at the University of Eindhoven did, where they essentially said, you know, for the next 3 years until we have a reasonable gender balance, we will only hire women, right? that is a very extreme measure that I think is probably not quite the right mechanism, but I think there are many other mechanisms. And the first thing is to just realize there is a problem. The second thing is to realize that there is an opportunity in overcoming the problem. And the third is to reasonably think about mechanisms that don't throw out the baby with the bathwater.
Another short answer, 2 short answers.
Oh, okay. Yeah, I just wanted to comment on this based on our experience at the school to achieve this 50% parity at the undergraduate computer science degree. In fact, we created an AI degree 2 years ago in which we also have 50% parity. The way that happened is it took maybe 10 years to make that happen. That means changing the admissions procedure and taking a very hard look at things that induce bias, even though we don't realize it. Let me give you just one example. In the US, there is something called AP placement, advanced placement. Those are courses that you can take in high school, for example, in computer science, in programming, and I think even in AI now, that give you an advantage in entering college. It took people many years to realize if we do this, we automatically decrease dramatically the number of female students who will apply. So from now on, we do not take EP placement courses into account at all. It doesn't matter if you place, at the top of the country in there. So the point is that there are many details like this that have to be looked at. It's not just one big thing.
Andreas, a quick answer,
Short
because we have to stop at 5 minutes before.
So I'm part of a program in Germany together with the Philological Association. So I'm a mentor of a high school, so dedicated to one high school. And at least once a year, I'm visiting the high school and to talk to the students over there, and also have events with female students. And my impression is, and it's a short answer, that we have an image problem. Yeah. And this image problem is caused by the education plans I can see in these high schools, which are made for males. And I think the capabilities and abilities of females are underrepresented in this education, and this also pushes the kind of competition among the students which are prioritizing the male students. That's my impression.
Yeah. So we have one question there, one question there, one question there. Very quick short question, short answer, please.
Thank you very much. From a public policy perspective, so we live in a world in which the bulk of the AI-related R&D is done by private firms, but maybe 40 countries have national AI strategies. So the question is, what research is required to move the field forward, but which the Amazons, Baidus, and Facebooks of the world are unlikely to focus on, and which should therefore be points of focus for governments?
Well, one item we emphasized in a recent position paper entitled Green AI is that obviously current AI methods are highly computationally intensive, require massive amounts of computers and data, and techniques like AutoML, which have huge advantages as you described, also, and neural architecture search and so on, also exacerbate that. However, we also need techniques that require less computation, both for the benefit of the planet, compute has been growing super exponentially, and for inclusiveness. We want it to be the case that an undergrad with a laptop in an emerging economy can still write a cutting-edge paper that appeared at a first-tier conference. Now, that's not the kind of research you typically expect to see out of the Google, Amazon, Facebook, et cetera, because they have the resources. They want to absorb the talent. So that's one where I think we need more from other institutions.
Bernard, a very short answer, because then we have to take at least one question.
So I think traditionally we have seen that some of the long-term research has been done in academic environments more successfully than in companies. But I worry that the companies are moving into that space as well. And right now, company positions are so attractive. I see it in my own PhD students that the power balance has changed, and many of the top people are getting into that field. So I think the bigger problem is if we want to have this research done in public research, we have to make sure that the positions in public research are sufficiently attractive that people still take them.
Dino, please.
I think that a concern that has been very well expressed in this forum is that for AI to be beneficial to the social system, to humans, actually what should be really assessed is the impact of systems made of people, both at individual and collective scale. A person that is making decisions together with an assistant, or a whole crowd in a town driving around assisted by personal assistant. So don't you think that a very fundamental core challenge for AI today, AI research, I belong to AI research, is somehow shifting from assessing the quality or the accuracy or the safety of systems in isolation to actually looking at the socio-technical compounds of what we are creating?
Thanks, Holger.
I think you're absolutely right with that, and particularly the way AI in Europe is moving towards the kind of AI that augments and enhances human capabilities rather than trying to wholesale replace them. I think what you say is extremely relevant, because we cannot look at these systems in a standalone manner. And that, by the way, also includes auto AI systems, which I talked about, which ultimately amplify human expertise, but the way they do that needs to be very critically measured, because otherwise you might end up with weaknesses at the meta level that propagate all the way through to applications. So there is a real challenge here, but also a great opportunity for kinds of research that might not be done in environments that believe in the kind of AI that just replaces human capabilities.
Great. Last question.
Yes, thank you. So I would have a very brief question for Professor Etzioni, who mentioned a very, very high-reaching goal, which is teaching machines common sense. We have seen this, haven't we, in the last 40 years, financed for 20 successive years, and it really didn't really get there. So for me, that part of the program looks like a really wholly different goal. If we could teach these systems to have common sense, oh my God, a lot of things could be done. So can you comment on the feasibility, the realism of that? Thank you.
Yes, so you're absolutely right that this is a major grand challenge for AI. The thing I would point out that actually as a community, we have not worked on it. So other than Doug Lennott, who has a very famous psych project that worked on it for some number of decades, the academic community has not worked on common sense. The methods that he used were really from the 80s, knowledge engineering, manual construction of knowledge, and very quickly he stopped publishing in the academic community. So I think it's fair to say that while we've recognized that the problem is an important one, up until recently, no one has been working on it. Now, what Yejin Choi and her team has done, even prior to joining AI2, is identifying that modern methods that have reached so much success in vision, NLP, and robotics, specifically deep learning, but also crowdsourcing, and so on, those methods give us a shot at acquiring, representing, and using common sense. So we're very early in this process, but the reason that we're more optimistic than the past is that we have very new methods at play. And crowdsourcing in particular is interesting here, because nobody asked, well, what is exactly common sense? And to define it in 5 seconds, common sense is what people have and machines don't, which of course means that crowdsourcing is a wonderful way to get labeled data. Thank you.
So I owe 3 seconds comment by Mark.
Okay, 3 seconds. I'm going back to an earlier question, or an earlier comment that said something to the effect that basically all of AI progress is now done, or much of AI progress is now done by the private sector. I've been hearing this since yesterday, including in high-level meetings. I think it is wrong, and it's a grave mistake to say this. ARPANET was created 50 years ago entirely on government funding. Self-driving started 35 years ago entirely on government initiatives in the US and in Germany. And it is true that progress is moving much faster now thanks to the private sector, but the real progress will still occur by sustained basic research.
Thank you very much. A good end. Thank you very much.